minimize metabolic cost per unit distance, with the 4-beat walk being optimal at slow speeds and the 2-beat run being optimal at intermediate speeds. But of course, we want to know, is there a mechanical reason why these particular gaits are optimal at these particular speeds? And one approach for this is to think about the collisional energetics of this. In this paper sort of solidified that idea. And so we do away with everything except for the point mass of the organism and pretend like it has impulsive legs. And this seems to work decently well for walking and running energetics in humans. But we can also try to apply this idea to quadrupeds as well. It turns out that if you think about how many legs do I need to reduce my energetic cost, well, if I just use all my legs as one leg, so I pronk around, then I have some cost. But if I use 2 beats per cycle, I have half that cost. And if I use 4 beats per cycle, I have a quarter of that cost. So it seems like the optimal strategy should be to use a 4-beat run in all cases. But then why do so many animals use a 2-beat run? And again, this is very broad. With very few exceptions, this occurs. So is there a physiological or mechanical reason why these organisms don't use a 4-beat run? Well, probably not. And the reason I don't think so is because there are rare examples of organisms that do use a 4-beat run at slow speeds. The Icelandic horse being probably the most famous example, which uses this gait called a tolt. So we can start to parse why trotting makes sense versus tolting if we stop thinking about a point mass and start thinking about a distributed mass. If you have a sequence of collisions, front, back, back, front, you're going to start pitching the body, and this is going to add a component of the energetics that is rotational. And if you dig into this component of the energetics, or this term in the energetics, it turns out that there's a particular normalization of the pitch moment of inertia, where this L is not the length of the rigid body of the trunk. It's actually the distance between the center of mass and your legs, or half the leg-to-leg distance. And I want to call this a name so I don't have to keep saying non-dimensional pitch moment of inertia. I'm going to call it the Murphy number because Carl Murphy in the 80s, when he was doing his PhD thesis, sort of found that this is an important number for thinking about the stability of bounding in robots. And it turns out that if that this number determines whether you'll move up more or whether you'll pitch more, and I'll explain what that means in a second. So if we have an impulse at one point of this body, we can ask what happens to the other set of legs. So we have an impulse in the back. Think about what happens in the front. Well, it turns out if your Murphy number is less than 1, that end will go down, right? Because part of this impulse will push the whole body up, and it will also make it spin. So if you add those together at this point, that point will go down. If your Murphy number is greater than 1, that point will go up. And if it's exactly 1, then your forelimbs are the instantaneous center of rotation, and they don't move at the instant of impulse. It also turns out that this is exactly the ratio between the translational and rotational energy imparted by the impulse if it's going from rest. And so if your Murphy number is less than 1, your rotational energy imparted by the impulse exceeds the translational energy, and if it's greater than 1, the opposite is true. So now this can explain where we might tolt instead of trot. And so if we just think about the translational energy, it is half, and we use 4 beats, we can save half the cost of a 2-beat gait. But now if we consider the rotational energy, this is proportional, inversely proportional to our mass or pitch moment of inertia. So we add those together, and it turns out that tolting and trotting have equal costs at a Murphy number of 1. So this is an interesting transition point where below this line, or left of this line, a 2-beat gait is optimal, and right of this line, a 4-beat gait is optimal. Okay, so now we can ask, well, where do animals lie in terms of the Murphy number? Well, basically, if you want a Murphy number less than 1, your radius of gyration needs to be within your 2 legs, and this is true for it seems most animals. You'd have to have pretty extreme morphology to be outside of this number. So they all have Murphy numbers less than 1. And that means they should trot, right? Mystery solved. Not at all. Okay, because we also know that these animals also use a 4-beat walking gait. So why would they use a 4B walking gait and a 2B running gait? That doesn't seem to make much sense. So if we think about what happens in walking, we have a 4B walking gait while, say, your shoulder limb is in stance, is vaulting. Your hind limbs are going to be in double stance and generate an impulse that will tend to rotate the body. If your Murphy number is less than 1, that shoulder point is going to go down. But that's completely fine because you can just apply an isometric contraction and prevent that limb from changing length, and so that limb does no work, right? So this is fine. You can keep vaulting, and you're doing great. If your Murphy number is greater than 1, that point is going to go up, and there's nothing you can do about that because you can't create a suction force pulling yourself into the ground. So inevitably, that limb has to do some work, right? So what this tells us is that we have sort of a quadrant of predictions. As we can think about what happens when we increase stride period or decrease speed. We can think about what happens when we change moment of inertia. And when our moment of inertia is sufficiently large, we should use a 4B running gait and a 2B walking gait. And when our moment of inertia is sufficiently small, which is the case for most mammals, we should use a 2B running gait and a 4B walking gait. Okay, so this is all hand-wavy heuristic arguments. Let's do one better with a quasi-realistic mechanical model of quadrupedal locomotion. As massless legs with prismatic actuators, and we can vary the pitch moment of inertia. We're going to optimize on limb work with a small force smoothing penalty. It's a single-phase optimization, so we let the optimizer decide the contact sequence, and afterwards we'll check the ground reaction forces post hoc to determine whether it's 2B or 4B. And we'll use stride length and speed relationship based on literature. Okay, so our prediction for a Murphy number less than 1 and a small speed is that we should use a 4B walk, and that's exactly what the simulator decides to do. And then at higher speeds, we should use a 2B run, and that is indeed what is optimal in this model. Okay, and then the opposite should be true when our Murphy number is greater than 1. We should use a 2B walk, and that is indeed what the simulator decides is optimal. And then we should use a 4B run, and again, this is what it decides to do. So those are just 4 examples. Let's fill out the space a little bit more. On the y-axis, we have our Murphy numbers, or non-dimensional pitch moment of inertia. There's a Murphy number of 1 right there. This is a log scale. And then on the x-axis, we have increasing stride period, or if you prefer thinking about speed, the speed is increasing from right to left. And what we do see is indeed these sort of 4 quadrants in the space, where in this lower corner, 4B walking is optimal. Then as we increase speed, decrease stride period, 2B running becomes optimal. But then the opposite is true. When our pitch moment of inertia is large, 2B walking is optimal and 4B running is optimal. Okay, so animals lie down here on this axis, and indeed they transition from a 4B walk to a 2B run. At least these 2 examples of animals. I don't want to say that all animals are either dogs or horses. But this idea also turns out to work for some robots. So this is Ramon, which has a very small pitch moment of inertia. And David Remy and his students sort of looked at what is the optimal gait for Ramon, and it turns out that a 4B walk is optimal, and then a 2B trot is optimal at higher speeds. Now this area over here is pretty empty. We'd like to fill it up. So the most extreme morphology we can get for mammals is probably the giraffe. That huge neck induces a very large pitch moment of inertia, and indeed the Murphy number is greater than 1. Despite this, our predictions were not exact initially, and it turns out that 4B walking is optimal for a short region above pitch moment of inertia greater than 1. And so it does turn out that giraffes do use a 4B walk. Now, our predictions are that they should not use a trot, and indeed they don't. But they don't use a 4B run either. Instead, they canter. So this model, because it's restricted to symmetrical gaits, cannot canter. But Jim Usherwood, who introduced me to these ideas, just published a paper, Journal of Experimental Zoology, where he explains how cantering fits into this idea. All right, so in future I'd like to add a few other extreme morphologies. These animals probably have Murphy numbers much larger than 1, but I don't know as much about their gait, so stay tuned on that front. So the take-home messages here is that the pitch moment of inertia is necessary to explain why 4B walking is optimal, 2B running is optimal for most mammals. We can't use point mass models to explain this, and I want you all to start thinking about the Murphy number and how it parameterizes the energetics of rotation versus translation, and how that relationship seems to switch for walking and running. All right, thank you very much.
So the obvious question is, have you yet tied a long board with weights on the ends to your dog? And if not, why not?
Yeah. So Jim Usherwood tried this once with one dog, and the dog just lay on the ground and did nothing. So yeah, that's an excellent.
That's minimizing energy too.
Yes, it's true. Yes, the task was not clear for the dog.
You have hot dog bits, and then it'll change the energy balance again.
Yeah, that's true. Now, David Lee, is probably in the audience. He has done experiments where he put masses on the redistributed the mass for the dog. So he did add some weight in the hips and then some weights at the shoulder. So maybe he has a better experimental method. But the issue is, of course, getting the radius of gyration outside that base of support, which is challenging. But yes, that would be a good experiment to do.
It's not challenging on robots.
That's true.
And so you're familiar with Avik Dey's work on bounding and pronking?
I'm not as familiar.
So he found a similar switchover at the same point. He was taking this more from a slip spring coupled oscillator.
Okay.
That it's actually, that's the stable. If you just say your front and back are bouncing.
Yeah.
If your Murphy number is less than 1, then you get bounding. If your Murphy number is greater than 1, you get pronking.
Okay. Yeah.
And this is board with some weights.
Now that's for stability, I assume.
That was passive stability for just oscillators.
So it's interesting because the stability seems to be flipped, right? So as I said before, if your Murphy number is less than 1, the 2-beat run is optimal, but it sounds like what you're saying is it's unstable. And then if your Murphy number is greater than 1, a 4-beat run is optimal, but it sounds like you're saying that's unstable. So the stability is flipped compared to the energetics.
But this was also with springs instead of.
Yeah. But my intuition is that it would be the same.
My second question is, what about that Icelandic horse?
Yes, that's an excellent question. So I don't know what's going on with the Icelandic horse. Now, the weird thing with the Icelandic horse is, I hope I'm getting this right, is that it seems to be genetically derived. So you can find a gene and you can turn it off, and then they stop pulsating. So there's some weird thing going on. Now, the thing with horses that you have to keep in mind is that they're highly artificially selected, and in some cases, they're selected for the gait. So there could be some things that are outside of natural evolution that are constraining their gait in some way. So it's something to think about.
I guess at higher speeds, I've seen obviously horses gallop. What is kind of the explanation?
Oh yeah, great. Another great question. So again, this model cannot gallop, but I do have a different model that can. We just our paper's in review right now, but you can see the preprint on bioRxiv. And that model can gallop, but it chooses not to. It prefers to trot all the time. And so in what seems to be the case is you need some sort of compliance in the torso to make galloping optimal. And so there's a different thing going on. The prevailing wisdom is that it has to be elastic in the spine, but our next step is to test if you can actually make galloping optimal if you have purely just active control in terms of making the spine flexible. Yeah.
Wonderful talk. Thank you. I was just thinking about nature, and a lot of small mammals trot over. They basically switch from walking to a half bound or gallop like gait, without trotting much at all.
Yeah.
And then a lot lot of large quadrupeds that have sort of heavier forelimbs than hind limbs don't do much trotting. They'll move right to a cantering, really gait.
Yeah.
So I'm just asking for your thoughts on those that kind of violate the basic pattern across the bottom of the plot.
Yeah, so I think with small animals, what you get is their Murphy numbers are going to be closer to 1. You might be able to see this if I back up enough. The reason is because their heads are so big relative to their body, and then with many mammals, they also have an extensive tail if they're a bit smaller as well. So I think what you get is you do get Murphy numbers that are closer to 1, and possibly exceeding 1 as well. But then there's also this other issue, which is that small mammals tend not to have an erect posture, so they have more of a crouch gait. So maybe internal torques of the limbs is going to play more of a role. So it does get a bit more complicated, I think. And then for larger animals, like the wildebeest, for example, is one prime example that doesn't seem to trot as well. If you actually look at it, it does kind of look more like this bottom example in terms of its head being sort of huge and sticking really far outside of its body. So I think there might be something there, and that it might in fact have a Murphy number greater than 1.
Hi. When I was looking at the giraffe, I was realizing that it probably has a huge spring in its neck, right? So part of that energy that is dissipated in the collision might not be dissipated in the collision, but might be stored in this neck by sort of letting his head bob, if you will,
so
back
head
and
bob,
forth.
yeah, so you're thinking a hip lip model for giraffes? Yeah, maybe. Now,
Do you think there's a big role there?
I don't know. So Chris Bazu and John Hutchinson just released a paper in JAB that sort of discusses this. Their thoughts are that the neck actually doesn't play much of a role. There's not actually much oscillation of the neck in walking, but who knows, right? Like if the spring is stiff enough, then maybe
They're still stored.
it is still storage. Yeah.
Sure.
Okay, let's thank our speaker again.